Computability is a subtle concept and difficult to define in a non-circular way. I could say a number is computable if you can compute it, for example, but that wouldn't be saying very much. What it means is basically that there's an effective procedure or process for writing it out digit by digit. For example, 4 is computable. I can write it out for you right now. There, I computed it. Now 10 to the 300 is also computable. I can write out a 1 followed by 300 zeros. I won't complete that right now, but eventually I would finish it, and the number would be computed. The number pi is also computable. There are algorithms that can output it digit by digit. So you can compute pi while it is an infinite decimal to whatever precision you want, as long as you're willing to pay for it. Because remember, the Landauer limit gives a lower bound on the energy consumption of any computation. So can we generalize this? Are there numbers that aren't computable? The answers are yes and yes. So now let me turn to a proper definition of computability. First, I have to draw a sharp distinction between syntax and semantics. Syntax is the words on the page. Semantics is the meaning. For example, suppose I send you a note. That says 2 plus 2. Now suppose you send me a note that says 4. We can both agree that that is a correct exchange. It's a valuable transaction. Except maybe I should pay you for computing things for me, but aside from that, it's correct. Now, suppose that I send you a note that says 2 plus 2 equals 4. And suppose that you sent me a note that says true. In both cases, you've performed computation for me. The reason that I bring these two examples up is to demonstrate the difference between symbols and their meaning. The message 2 plus 2 equals 4 is just a 5-letter word. The message true is a meaning, or can be derived from the meaning. Computation, then, is the ability to read a word and reduce it to its core meaning. A word like pi might be defined as the ratio of the circumference of a circle to its diameter, and a sufficiently clever computer can produce as many digits as you ask for. The question then comes up, how is meaning learned? In other words, how do we know that 2 plus 2 equals 4 has the same meaning or can be reduced to true? And how do we know that 2 plus 2 equals, or can be reduced to 4? How do we come to agree on that? I'm not going to go into that, but what I will do is explain what meaning means to a computer. To a computer, you enter a computer program and it executes. While it's running, it may produce some data. However, some computer programs get lost and start running endlessly without producing any data at all. It turns out there's a sharp distinction between well-behaved languages and non-well-behaved or Turing-complete languages. There are languages in which every program either halts or produces output. These are the well-behaved languages, and there are languages in which some programs crash, that is, exit abnormally, or run endlessly without ever producing data. These are the Turing-complete languages. These are the languages where software developers live. Because, well, in well-behaved languages, while they're a good guidestone for theory, they're typically not useful for programming. The safety, so to speak, of the guarantee that all programs either halt or run productively places certain constraints on the shape of a computer program and makes it difficult to write long, large-scale programs. They're longer than the corresponding large-scale program in a Turing-complete language. And some programs can't be written at all. For any well-behaved language, there are some programs that are valid programs but can't be written in the language because of this band gap. Turing-complete languages, on the other hand, allow you to write any program. Any program can be written in any Turing-complete language. Of course, to us, the whole computer program is syntax. Typically, the well-behaved languages are used to represent data in practice, and these Turing-complete languages are used to represent algorithms. Now, the computer program itself is data. Computer programming languages are usually specified in well-behaved languages. This is because it's very important that if you have a computer program, it is very important to be able to tell that it's a computer program and which one it is. So, programming languages are usually specified in well-behaved languages. But then the programming languages themselves are not well-behaved. Now, the well-behaved parts are typically, they represent syntax, as I've alluded to already, since programming languages are syntax. And the Turing-complete languages are, they have meaning associated with them, or semantics. Now, of course, to us, the whole program is syntax. Where the semantics actually comes in is on contact with the laws of physics. The electromagnetism in your processor kicks into gear and breathes meaning into the program code. the meaning of the program is derived from its interaction with the electromagnetic laws that occur, or processes that occur in your CPU. So the meaning is associated with the understanding of physics. Anyway, part of what it means for Turing-complete languages to be dangerous is that there is no program in any language that can tell whether a program is well-behaved. This is called the halting problem. Of course, if it's written in a well-behaved language, then it must be well-behaved. But if it's written in a Turing-complete language, then it may not be well-behaved. So already we have something that, in a sense, is non-computable, namely whether a program is well-behaved. But let's see if we can find a number that's non-computable. Here's an example of one. Take any Turing-complete language and sequence all of the programs in it from shortest to longest. You may also sequence them alphabetically. Now we're going to define the following number. This is the decimal expansion of the number. N1, N2, and so on are digits. Now, we're going to say the ith digit, Ni, is equal to 0 if Pi, the ith program, is well-behaved. And likewise, we set Ni equals 1, where we define Ni equals 1 if Pi is not well-behaved. Now, if we could compute this number, then we could solve the halting problem. But the halting problem is undecidable, so this number is not computable. There are many more non-computable numbers, and there are also non-computable functions, including some that grow faster than any computable function. I invite you to learn more about these, and until next time.